Hi, we are going to start with the analog electronics part. And in this first lecture, we are going to cover about rectifiers, including both half wave and full wave, as well as bridge rectifier. And next, we will see about the rectified power supply. So let's start. So let's start with what is rectifier. So basically, what we need is we need we have the AC power supplies or alternating current power supplies. But for the implementation or practical purpose, we need to use the DC supply or direct current, something like this, a 5 volt DC or something like this. So what we need to have is we need to design some circuit which can convert this AC into DC. For example, a simple diode. A simple diode can have a sinusoidal wave as input, where average value is 0, and output it can give up some, let's say, zero point 0.7 volt or some voltage signal with some average value. So we will discuss about rectifiers in detail. Let me show a simple half wave rectifier diagram. So this is a simple half wave rectifier. We have a step down transformer. That means the primary coil has more windings than the secondary. On the primary side, we have a standard 50 Hz AC supply. On the secondary side, we have connected a diode and a load resistance. So if we draw the equivalent circuit diagram, it looks like this. AC source, a diode, forward bias diode, and assuming that this is a ideal diode, and a load resistance. So if we represent the Vs as a simple sinusoidal wave with magnitude Vm and frequency f, so it can be written as Vs equals to Vm sin omega t. And then for now, see that for the positive cycle, the diode will be forward biased, and for the negative cycle, the diode will be reverse biased. So this leads to that id will be Vm by RL sin omega t for the time of 0 to pi, when omega t is moving from 0 to pi, and the same id will be equals to 0 for the pi to 2 pi cycle. Here 0 to 180 is pi, and then 180 to 360, that is 2 pi. So similarly, this id has two parts. Similarly, if we write about the load voltage, which is the voltage across load resistance, then it will also be a two phase vector, which will be 0 to pi. Between 0 to pi, it will be Vm sin omega t, and for pi to 2 pi, it will be 0. Now what we will have is, if we calculate the DC value of this complete current, so this IDC will be over the complete time period, that is 2 pi. We integrate it with respect to the time, so it will be IT respect to d omega t. And if you solve this, you will get IDC equals to Im by pi, or you can say 0.318 times Im. So for the half wave rectifier, we have IDC equals to VDC upon RL, where VDC is given by maximum voltage upon pi, right? These are the important DC values for current and voltages. Next, we will look at other fundamental properties which are used for rectifiers. Now, if the frequency of operation we are taking as omega equals to 2 pi f, so if this f is the fundamental frequency, then we term we have a term called ripple frequency. Ripple frequency is 2 omega radian per second, or you can say 2f, because you see, for one input cycle, the output will be the output will be present only for positive cycle. Then this will not be there will be no output for the negative cycle. Then again for next positive half it will have. So here the frequency is doubled in case of half wave rectifier. This is very important, that for half wave rectifier, ripple frequency is twice the fundamental frequency. And we calculate a ripple factor. Ripple factor is given by gamma, that is RMS value of AC component of load voltage divided by DC component of load voltage. So for the half wave rectifier, the ripple factor is constant as 1.21. And similarly, we have a term called form factor. So this form factor is given by the load current RMS value divided by load current DC value. So this form factor for half wave rectifier is pi by 2 or 1.57. So these are the important parameters which are directly asked in exams, like what are the ripple factor or form factor for half wave or full wave rectifier or any kind of rectifier. Apart from this, every rectifier has power conversion efficiency. So this is represented by eta, which is given by DC output power upon input power. And since this is efficiency, so we multiply it by 100. Now this DC output power is basically I square RL, where IEDC is used at the load. And input power is AC power, so we integrate it from 0 to 2 pi, the source voltage to drain current into, and integrate it with respect to omega t. So this AC power basically is given by IRMS square into the source resistance plus the load resistance. So for this half wave rectifier, the power efficiency is given by 2 by pi whole square over 1 plus RS plus RF by RL. And similarly, if we talk about percentage of voltage regulation, is how efficiently the rectifier is regulating the voltage. So this is given by RS plus RF by RL.